Algorithm design. Introduction. Definition of algorithm. An algorithm is a step by step procedure for solving a problem or accomplishing a task. It involves a series of well defined instructions. Importance of algorithm design. Efficiency. Algorithms optimize performance, making processes faster and more efficient. Scalability. Good algorithms handle larger datasets effectively. Optimization helps in finding the best solution among many. Types of algorithm based on the design approach. Divide and conquer. It breaks the problem into smaller subproblems, solves them recursively, and combines the result. Dynamic programming. It solves problems by breaking down into simpler subproblems and storing the result. Algorithm. Build up a solution piece by piece, always choosing the next piece with the most immediate benefit. Backtracking tries to build a solution incrementally, removing solutions that fail to satisfy the constraints. Branch and bound, it enumerates candidate solutions by measuring of state space search. Divide and conquer in detail. Concept is that divide the problem into smaller subproblems, solve each subproblems recursively, and then combine the solution to solve the original problem. Examples include merge sort and quicksort. Merge sort will split the array into half, recursively sort them, and merges the sorted halves. Quicksort select a pivot, partitions the array around the pivot, and recursively sort the partitions. Dynamic programming. It solves problems by breaking them down into simpler subproblems and sorting the result of subproblems to avoid computing the same result multiple times. Examples include Fibonacci sequence and knapsack problem. Fibonacci sequence stores previously computed values to avoid redundant calculations. Knapsack problem uses a table to store the maximum value that can be obtained with given weights and values. Then greedy algorithm, it make the locally optimal choice at each step with the hope of finding the global optimum. Examples include Huffman coding, which built a binary tree used for data compression, and Prim's and Kruskal's algorithm, which find the minimum spanning tree in a graph. Then backtracking, it built a solution incrementally, abandoning a path as soon as it determines that this path cannot possibly be a valid solution. Its examples include n-queens problem and Sudoku solver. N-queens problem places the queens on a chessboard such that no two queens threaten each other. Sudoku solver fill in the Sudoku board while backtracking when a number doesn't fit. Then branch and bound. The concept systematically considers candidate solutions, pruning branches that cannot yield better solutions than the current best. Examples traveling salesman problem and integer programming. Traveling salesman problem uses bounds to limit the number of paths explored, and integer programming prunes parts of the search tree that don't lead to a better solutions. Algorithm analysis. Its importance include predict performance and compare efficiency. Predict performance is understand how algorithms will perform as input size grow. Compare efficiency helps in choosing the most efficient algorithm for a task. Key matrices of algorithm analysis is time complexity and space complexity. Time complexity is the amount of time an algorithm takes to complete as a function of the input size. Then space complexity, it is the amount of memory an algorithm uses as a function of the input size. Time complexity. It is the measure of the time taken by an algorithm to run as a function of the length of the input. Common notations include worst case scenario, best case scenario, and average case scenarios. Examples order of n for linear time, order of log n for logarithmic time, order of n square for quadratic time. space complexity. It is the measure of the amount of working storage an algorithm needs. Its examples include order of 1 for constant space, order of n for linear space, and order of n square for quadratic space. Then case studies of uh, it includes sorting algorithm and graph algorithms. In sorting algorithm include bubble sort and merge sort. In bubble sort, simple but it is very inefficient. And merge sort is efficient with order of n log n complexity. Then graph algorithms, it includes Dijkstra's algorithm and a Bellman-Ford algorithm. Dijkstra's algorithm find the shortest path with non-negative weights. Bellman-Ford algorithm handles negative weights but it is slower. Best practices in algorithm design. Understand the problem, choose the right approach, optimize for efficiency. So in understanding the problem, clearly defines the problem specifications and constraints and identify the goals and requirements. In choosing the right approach, select the appropriate algorithm design techniques based on this problem type. Consider trade-offs between different approaches. Then optimize for efficiency include aim to minimize time and space complexity, use data structures effectively to improve performance. Thank you.